reactions. And one of the last things I told you when we reviewed the chapter on Friday was that this said that these reagents and reactions have kind of revolutionized the way pharmaceutical drugs are formed. So I'm reading various research journals, and I just happened on Saturday to be looking at, if you can read this, Angewandte Chemie International Edition 2016, whatever. So this is the premier European chemistry journal, published in English for the international edition and in German. So I've written the English one, obviously. And look at what they have here. So these are fairly complicated structures, but I don't know if you can read this down here. It says first-in-class HCV drug candidate, flupravir, and currently approved HCV drugs prepared via ring-closing metathesis. Okay, so these are drugs. HCV is human hepatitis C virus. Okay, so there are three kinds of hepatitis: A, B, and C. Hawaii, by the way, as you may or may not know, has the unfortunate distinction of having the highest per capita incidence of both hepatitis infection and also related to that liver cancer. And so hepatitis C is the one that's typically transmitted by blood, contaminated blood, so intravenous drugs, blood transfusions, and sex. And A and B are usually, I guess, transmitted by contaminated food. These, so as you may also not know or know it, antiviral drugs viruses are a lot harder to kill than bacteria. So antiviral drugs are kind of few and far between. Now, notice these structures, they're complicated, right? These are made through chemical synthesis one step at a time, but all of them are made with a ring-closing metathesis step that forms the big ring. Notice these all have a big ring here. And so I thought you'd be interested in seeing that. Also, notice how many asymmetric centers you have here. 1, 2, 3, 4, 5 for this one. For this one, a few more, and so on. And so these are not easy compounds to make. As a result, the drugs that you get are fairly expensive. So the ring-closing metathesis step is kind of summarized here. This HI or NG, that's shorthand for the catalyst that was used, different catalysts for different compounds. Why different catalysts for different compounds? No rhyme, no reason. These are optimized conditions, and they're optimized through trial and error. Okay, so 5.3 mole percent of the catalyst, fairly high catalyst load, but look, the yield is 87%. So good yield. The bond that is formed in the metathesis is indicated here, the broken line in each case, and the conditions are given. Notice that it is dilute, 0.01 molar, right? Now, why dilute? Well, for the reason that I indicated, because if you want the ring to form, you want collisions not to take place between two molecules. You want collisions to only take place within the same molecule. So you can favor that by doing the reaction under dilute conditions. And it takes heating to 80 degrees for 20 hours and so on. And so you'll notice that all of these compounds can be made fairly nicely using these conditions. And also, you'll notice that the catalyst load can differ by, in this case, a factor of 10. And that just, it's just the particularities of that problem. In the same review, and this was a review article, in the same review article, they addressed another issue that was brought up, I think, by Ms. Elise in this class, and that is using chemistry for formation of fuels, right? And so linalool this is a naturally occurring terpene. It follows the terpene rule that we talked about. And you do a ring-closing metathesis here to form that 5-membered ring. Now to go from here to there are three steps that you know, okay? And I'll tell you which ones they are. The first step is an acid-catalyzed alcohol dehydration. The second reaction is a Diels-Alder reaction. And the third reaction is the catalytic hydrogenation. So those three steps will convert, and so now you know all the steps because you know metalysis is step 2. So presumably you could understand this chemistry just fine. This turns out to be a fuel that you can use in jet engines without any kind of modification to the jet engine, which is a big deal. So there's a big push now to find alternatives to petroleum particularly for aviation fuels. And the reason for that is because we're not probably going to see, we'll see electric surface vehicles for sure, but we're not likely to see commercial electric airplanes anytime soon, and so that's why this is useful. Anyway, I thought you'd be interested because you sometimes don't, it's difficult for you, I think, sometimes to appreciate that the things we learn in this class actually do have a bearing on, very practical problems and their solutions. So let's make this a little bit smaller so we can see it. Okay, so last time we left off talking about nucleophilic additions to carbonyls. And I said that when an electron pair from the nucleophile reacts with the carbonyl group, then that electron pair has to. It's got feedback, doesn't it? Does this have feedback?
No, you're fine.
So the electron pair has to find a home, so to speak. So it needs to enter the pi star, the empty antibonding orbital. And as the reaction proceeds, you end up forming a sigma bond here. This ends up rehybridizing from sp2 to sp3. And the bond angles change from 120 to close to the tetrahedral angle. Now we've seen something similar to this when we talked about SN2 displacements, right? And we said that, well, it goes from an sp3 then to an sp2 in the transition state, and then it goes back to sp3 in the product. It's not quite the same, but this rehybridization of a carbon atom during a reaction is something you have seen before. Okay, so then we talked about hydrate formation, and we said that, well, this is maybe, it sounds a little bit like a kind of a very useful or very interesting reaction, water reacting with carbonyl. I mean, it turns out it does have relevance. It has relevance, actually a lot of biological relevance, in the area of sugar chemistry. Sugars are used, of course, are the backbone for your RNA and your DNA, right? So this chemistry is actually important. So you get proton transfer. The electron pair here is basic. That activates this carbonyl group towards nucleophilic attack. It activates it because if I show the other resonance structure of this thing, I have a full positive charge on that carbon atom. And so I end up with this tetrahedral intermediate. And so this electron pair enters the pi star and so on. And then proton transfers give this compound, which is now not the ketone, but it's the hydrate, so it's the ketone plus water. Now, in the case of acetone, which is what I've shown here, the equilibrium overwhelmingly favors acetone. However, if I put 3 fluorine groups there, then the equilibrium pushes to the right. And if I have an aldehyde here, then that pushes the equilibrium to the right. And so something goes on here that we need to understand, right? And if I have something like acetaldehyde, for example, then the hydrate is the major compound. Now, so that's just what I said. Acetone, the equilibrium overwhelmingly favors the ketone. Now, what influences the position of equilibrium? And so the general rule, before we go through that, the general rule is that anything that destabilizes the carbonyl compound will favor the hydrate. In fact, anything that destabilizes the carbonyl group will favor any kind of nucleophilic adduct to the carbonyl. Makes sense, right? Nothing special about water as a nucleophile. If you destabilize the starting material, any nucleophile you add to it will add better than if you have a very stable carbonyl. If you have a very stable carbonyl, it's way down here in energy. And you've got to go way up here to get onto the transition state. If it's destabilized, then instead of being way down here, the carbonyl is up here, there's a shorter distance to reach to the transition state, so of course reaction state phase is better. So aldehydes have a more more favorable equilibrium for addition than ketones. Why is that? Well, think of what we just said about the carbonyl group. Okay, so we have a carbonyl group. Here's a ketone, and here's an aldehyde. Okay, and if I show the resonance structure here, what do I have? I have this kind of a tertiary cation. If I show the resonance structure here, I have this kind of a secondary cation. Now, that's a very simple-minded argument, but it actually holds. Okay, so that tells you that the aldehyde carbonyls are less stable than ketone carbonyls, and therefore more reactive. Okay, good. Electron withdrawing groups on the alpha carbon atom make the carbonyl addition more favorable. So this also will be stable. So imagine then that I take this already unstable carbonyl, and I put a fluorine atom on the adjacent carbon atom. So if I put a fluorine atom, then I further destabilize that because the fluorine is pulling electron density out of this sigma bond. So I have a delta plus there next to a plus charge there. So yeah, electron withdrawing groups are going to have the effect of amplifying the reactivity. And then, of course, electron donating groups are going to have just the opposite effect, because those are going to stabilize that charged, that polar resonance form. Now, the interesting thing is that the rates follow the same trends as the equilibria, which is nice. They didn't have to, but they do. And so if we have an unstable carbonyl compound, then we know not only that the equilibrium will favor the adduct, but it's going to be a fast reaction too. So any factor that destabilizes the ketone or the aldehyde will result in a fast addition and a favorable equilibrium. Okay, so we end up lowering the barrier, the distance to the barrier. So one way to think about that graphically is usually with one of these energy diagrams. And so if I look at acetone versus hexafluoroacetone, this is more stable, that's less stable. Why is this less stable? Well, for the reason that I indicated. So fluorine's there, they pull electron density out, you already have a positive charge. So what that means is that if I compare the energy, the free energy of acetone and hexafluoroacetone, this is higher. On the other hand, for the hydrates, there's not a huge difference, because why? Well, because now this is no longer a delta plus carbon atom. Once I have the hydrate, I no longer have a carbonyl that puts a partial positive charge on that carbon atom. And so this kind of tells you, in a graphical way, what I just mentioned earlier on. So closing the energy gap when you start and build a product, you favor the product in the equilibrium. Now, we talk about features that destabilize the ketone or the aldehyde, but what about structural features that stabilize it? And so, once again, well, we kind of mentioned that, electron donating substitution. So anything that will stabilize a cation will stabilize the ketone. So in other words, if I have electron donating groups here, if I have an aromatic ring, if I have a double bond here, anything that can stabilize through either resonance or through induction, this positive charge will stabilize the ketone, and if it stabilizes the ketone, what does that mean? It means that nucleophilic additions to that carbonyl are going to be slow, and the equilibrium will not go to completion. So if R1 and R2, either one of them or both, are electron donating, they're going to stabilize this ketone. Electron withdrawing will destabilize. So we've said it now 3 or 4 times. So, you know, it's kind of easy to tell just by looking at the structure whether you're going to have a reaction that's going to be a good reaction, fast reaction, or one that, you know, is just never going to go. So this also explains why aldehydes are more reactive than ketones, just from carbocation stability. So here's what I said about groups that are conjugated with the carbonyl. So if you have a phenyl group attached to a ketone, if you have a phenone, or if you have an alpha-beta unsaturated ketone, then electron density from the pi orbitals can be donated into the carbonyl, stabilizing it and slowing down the rate of nucleophilic addition. Now, there's also a steric effect. We probably won't see this as much as the electronic effect. In the case of ketones, okay, so here's the deal. If R1 and R2 are alkyl groups, right, and in the starting material, you have a 120-degree angle here. In the product, you have something that's closer to 110 degrees, right? So you've pushed, so in the product, because this is sp3, R1 and R2, the angle between them is closed, which means that they're closer together. Now, if those things are big, then you're going to have a van der Waals problem in the product that you don't have in the starting material. Because you have two large groups now that have been compressed together. So that also, if these are huge, and by huge I mean something like tertiary alkyl, then yes, the nucleophilic addition of the ketone will be slower than if they were not large. So van der Waals repulsions in the product will be experienced in the transition state leading to the product. The way to think about it is this: any nucleophile that approaches that carbonyl is going to bump into those this tertiary alkyl groups long before it forms a bond. And so that's going to raise the energy of that transition state. Okay, now let's look at maybe some reactions that are more more useful and more generally useful. And the first one is it's a very simple reaction, but very important: reduction. Now, we've seen lots of reductions, haven't we? We've seen reductions of double bonds to form alkenes to go to alkanes. We've seen reductions of alkynes to go either all the way to alkanes or to alkenes. We've seen diene reductions, we've seen Birch reductions, we've seen a whole bunch of them. So here, it's a very simple reaction. You think of the reducing agent as H- hydride. Now, this gets a little bit complicated, well, not complicated, confusing, because not all hydrides we use that term promiscuously, and not all hydrides are the same. Here, let me explain. So you have seen this hydride, sodium hydride. And you have seen this, and where you have seen this is what? In the Williamson ether synthesis. So you take sodium hydride, you treat an alcohol, typically a primary alcohol with that. What happens? You get an acid-base reaction. You get this is a strong base. That gives you hydrogen gas that goes flying out, and you get the alkoxide. And this reaction takes place from left to right. There's no equilibrium. This is a very strong base. Hydrogen exits from the reaction flash. You get quantitative conversion of alcohol to alkoxide. And then you can treat this with iodomethane or whatever you want, get your SN2 reaction, and that will give you, in the Williamson ether synthesis, it will give you the ether. And because you start out with sodium hydride, you'll have sodium iodide as your byproduct. Okay? So this is sodium hydride. Sodium hydride is a strong base. It hardly ever acts as a reducing agent. Okay? So now we look at these kinds of hydrides. This is not sodium hydride. Okay? So just so we understand, not sodium hydride. This is going to be typically sodium borohydride, this stuff here, which we still call it a hydride, but it ain't the same as sodium hydride, very different species, or lithium aluminum hydride, which is a reducing agent, but these two also are not the same at all, as you will see. And so even though we all call them hydrides, they're not exactly the same reagent because none of them are really a free H-. Okay? So that's the reason. There's a good reason. The reason is that in each case, the hydride is different because it's never H- all by itself. And so, but it helps to think of it as H- all by itself. And so we're going to do that. But I want you to know that this is just for us to think about. It's not reality. Okay? So we think about protonating the carbonyl and then H- attacking. Now obviously this is BS, because if I have H+ and H- in the same reaction, strong acid, strong base, The fast thing that's going to happen before anything else is going to happen is those two are going to get together and you're going to spit out H2, right? Because proton transfers are typically the fastest thing going. And so clearly, this can't be right. This has to be an approximation of reality. But it's a good way to think about it. This process, by the way, is irreversible. Once you reduce it, you don't get an equilibrium here. Why? Well, because if you were to get an equilibrium, you'd have to spit out from the tetrahedral intermediate, you'd have to spit out H minus. H minus is no kind of leaving group because it's a very, very strong base. So once it goes this way, it's finished. Okay? So now let's take a little bit closer look. So we never have free hydride. We have reagents that react as if they were free hydride. And the two that we're going to look at most commonly are sodium borohydride and lithium aluminum hydride. Are there others? Yes, plenty of others. Do they have the same kind of reactivity? Well, no. You know, they have slightly different reactivities. And some are good for some things, and some are good for reducing other functional groups. But that we don't need to worry about right now. Let's just take a look at the most common one, which is sodium borohydride. So I've tried to highlight the hydride here. So if I take 4 molecules of cyclohexanone and 1 molecule of sodium borohydride, in methanol as solvent, very important, I end up reducing the ketone to a secondary alcohol. The hydrogen atom here, that was provided by sodium borohydride, and all 4 of those borohydride atoms are borohydride hydrogen atoms. All 4 hydrogens are reactive. So it's not like, you know, you react one, you throw away the other 3. They're all reactive. Now, had I started with sodium borobutyride, commercially available, expensive but not prohibitively so, had I started out not with sodium borohydride, but with sodium borobutyride, with deuteriums here, then of course the deuterium is going to end up right there, and I'm going to have a deuterated alcohol, okay? And so that's how you can tell, by labeling your borohydride, you can tell that yes, this is provided by the sodium borohydride, not by methanol or something else. Okay, so sodium borohydride, okay, so we have sodium borohydride and methanol. Now methanol is reasonably acidic. Hydride, H minus, all by itself, is extremely basic. I don't know what, you know, it's got, hydrogen has a pKa of God knows, you know, 50, 60, who knows. So the fact that these don't react explosively tells you that you don't have free hydride here. Sodium borohydride does react slowly with methanol. And it will give you, so what you will get from sodium borohydride and methanol is you'll get sodium, if one hydride reacts, you'll get a molecule of hydrogen gas, and you'll end up with a methoxy group bonded to boron. And then another one can react, and another one, and another one. But these reactions are slow. And the fact that these reactions are slow tells you that, no, we don't have free hydride. So what you have is BH4 minus. Okay? Now it makes sense, because if you ever did have free hydride, then that would mean that you have also a trivalent boron species. Trivalent boron is a very strong Lewis acid. If you have free hydride, those two are going to react. So it all should make sense. Okay, now lithium aluminum hydride is the same chemistry. So you can say, well, you know, why do we need 2 reagents to do the same thing? And there's validity to that argument, but lithium aluminum hydride does a heck of a lot more stuff and different stuff than sodium borohydride. However, it's also a lot more dangerous. So sodium borohydride is something that even an undergraduate who's not particularly well trained in the lab can use and not kill himself or herself. Lithium aluminum hydride, if it's a powder and it is reactive enough that it will catch fire in air, okay? And so this stuff is dangerous. And so you have to use it under strictly anhydrous conditions. So you use this not in methanol, because it'll react with methanol, you use this in ether. If If you do that, you get the same kind of reaction where the hydrogen is provided by the LAH. LAH is the acronym for this. So they react to do the same thing. I mean, I could have taken this as an example, but these two reactions are essentially the same in terms of the product that they give. Okay. Now, all four hydrogen atoms on the aluminum are reactive, and they react sequentially. And so once I transfer one, I still have 3 red hydrogen atoms here that are reactive, that can react with more molecule of starting material. Now I have 2, and then it can keep going. You need to reproduce these mechanisms on your own to make sure that you know what's going on, okay? So both of these reagents will transfer all 4 of the hydrogen atoms. Now, in the case of the lithium aluminum hydride, it turns out that the lithium ion is important. So you have lithium aluminum hydride, you have lithium present. Now, metal ions, okay, and especially lithium. What do we know about lithium? We know it's a Lewis acid, right? And so what the lithium is doing here is it is coordinating with the carbonyl and activating it and making it more reactive towards the hydride. And so with sodium borohydride, you don't have a lithium ion, you have a sodium ion. Sodium is much less good at this because it's not as electropositive. And so that's why you need that's why sodium borohydride reactions need to be done in methanol, or sometimes aqueous methanol. Why is that? Well, here's why. Here's how you activate the ketone with LAH. Lithium is there, you have an activated ketone. With sodium borohydride, you don't have an activated ketone. So that's why you have to do it in methanol, and then these hydrogen bonds that form from the methanol or ethanol or water, any hydroxylic solvent, those hydrogen bonds activate the carbonyl. And so if you try to do a sodium borohydride reaction in ether, for example, nothing happens. Why does nothing happen? Well, because ether can't form hydrogen bonds to carbonyl. The carbonyl is not activated, and sodium borohydride is not nearly reactive enough to go for the carbon atom if it's not activated through this kind of hydrogen bonding. And so here's another example where solvent is not an innocent bystander. Okay, so solvent here is not innocent. It's doing something. And it's doing something very important. So we always need to remind ourselves that, you know, we don't often talk about exactly what the role of the solvent is, but very often the solvent plays an absolutely critical role in the success of a reaction. Here's another example of that. Okay? Now, I said that sodium borohydride reduces ketones to alcohols. Of course, it reduces aldehydes to alcohols too, and it does so faster than ketones because aldehydes are more reactive than ketones. And it does other things too, which we don't need to talk about. Now, lithium aluminum hydride, more reactive, that will reduce a lot of other functional groups. It will reduce nitros down to amines. It will reduce sulfonate esters to alcohols or to hydrocarbons. It will reduce esters to primary alcohols. It will reduce nitriles to primary amines. And we're going to see some of this. So this is a very reactive species that will do lots of things. Now, that immediately tells you why you need something, why it's useful to have something like sodium borohydride. Because let's just say that I have the following ketone, okay? And it doesn't have to be aromatic, but you know. Let's say I have this ketone, okay, and I want to reduce this carbonyl group to the secondary alcohol. I can't use lithium aluminum hydride, because if I do, the nitro group's going to get reduced too. But with sodium borohydride, I can. It will only go for the carbonyl. And so the fact that I have these two reagents gives me selectivity, the power to select for one functional group over another. So sodium borohydride, much more selective, i.e. less reactive, therefore it discriminates to a greater degree. Now, sodium borohydride will do some surprising things, but we don't need to go through that. Now, selectivity is a big issue, right? Because you don't want to be put in a position of having to effect a kind of a chemical change, and then it changes not only the functional group you're looking at, but everything else there, and then you're kind of screwed. You can see that if you think about the complexity of these molecules we looked at this morning. If you look at these molecules, you'll see that they've got multiple reducible functional groups. You know, you have a sulfone here, you have an amide, another amide, another amide, another, this is a carbamate, this is a carbamate, we don't know that yet. But so you have different kinds of functional groups, and you have double bond in one of them. So you want to be able, especially if you're going to make something synthetically of this complexity, you want to be able to get in there, not with a sledgehammer, but with a scalpel, right? And so that's why it's useful to have reagents that are selective for one over the other. Now, the other way that we know to reduce things is by catalytic hydrogenation. So remember that when we talked about converting an alkene to an alkane, how did we do that? Well, we put the alkene in a flask with some solvent. We put a little bit of palladium on carbon or platinum on carbon catalyst, and then we either bubbled hydrogen gas through the solution, or we took a regular party balloon, filled it up with hydrogen, stuck it over the flask, and stirred it for a while. And if we did that, then we would end up saturating the double bond, but typically not saturating the carbonyl. So catalytic hydrogenation will always reduce the C double bond C, almost always. But C double bonds O usually not reduce, at least not quickly. And so the mechanisms are, of course, very different. And so you're able now to go from here to there, or if I treat this with sodium borohydride, I can preserve the double bond and reduce the ketone. I do either one I want. Okay. So that was the reaction of what? That was the reaction of hydride with carbonyl groups. Of course, it's not free hydride, but it behaves as if it was free hydride. Okay? So now let's look at something that's almost the same. Not quite the same, but almost the same. And this is the reaction of carbonyl groups with Grignard reagents and related reagents. What's related to a Grignard reagent? What's its first cousin? Well, an alkyl lithium, for example. I mean, those are the ones that we've seen in the past. And yes, alkyl lithiums and Grignards will react in almost the same way. And so, how do we make Grignard reagents? Well, let's remember, you take an alkyl halide, you treat it in an ether solvent with magnesium metal, and you get this ethyl magnesium bromide, which, although it isn't, it reacts as if it's ethyl minus magnesium bromine plus, bromomagnesium plus. This is a strong base, but it's also a good nucleophile, very strong nucleophile. And this is a Lewis acid. And so I have the same kind of situation that we had with what? With lithium aluminum hydride. Lithium plus was the Lewis acid. Hydride was the nucleophile. Here's the Lewis acid, that's the nucleophile. So, no surprise, the electron pair on the carbonyl engages the Lewis acid, and the ethyl group is transferred to the carbonyl to give you a red carbon-carbon bond in a tertiary alcohol, or alkoxide, which is converted to the tertiary alcohol by treatment with aqueous acid and Orca. So, if I can add hydride to this carbonyl, or I can add an alkyl group derived from a Grignard or from a alkyl lithium. Now, one thing you need to kind of pay attention to here is what I've highlighted. This reaction makes a new carbon-carbon bond. What did we say about carbon-carbon bond forming reactions? Yeah, because there aren't all that many. So here's another one. And so this is going to turn out to be an important reaction for us. Alkyl lithiums work pretty much the same way. Lithium is the Lewis acid. Here, methyl is the nucleophile. So you form this bond here. And I haven't shown, if you treat this with aqueous acid, of course you're going to end up with a tertiary alcohol, not the alkoxide. Okay. Now, you may remember, or maybe you don't, that lithium acetyl, or sodium, lithium, sodium, potassium acetylides are also good nucleophiles. And so this is a way to form a bond to a carbonyl as well. And the acetylides are more easily formed because you can form those by deprotonating the corresponding acetylene. So let's talk about sodium acetylide just for a tiny moment here. So sodium acetylide. How did I make sodium acetylide? Well, I made that from acetylene, and I can make that from sodium hydride or sodium amide. Okay? And these are strong bases. This is quite acidic, and so I can do the deprotonation. It's a little bit easier to do than making methyl lithium or even the Grignard. So the acetylides are easy to come by. Just as the case was with hydride, all of these additions are irreversible. So you don't end up with an equilibrium of carbonyl plus tertiary alcohol or tertiary alkoxide. Why are they irreversible? Well, because the C- compound that you have to spit out from the tetrahedral intermediate is a very strong base, and so it's not a leaving group. And so once you form that red bond, it forms completely and irreversibly, because this is not a leaving group. Okay? Now that we know this chemistry, we can talk about 1 and 2 carbon homologation reactions. So what does homologation mean? Well, it means if I start with a chain of N carbon atoms, I end up with a chain of N plus 1. So that would be a 1 carbon homologation. If it's a 2 carbon homologation, it means I start with a chain of N carbon atoms and I end up with a chain of N plus 2 carbon atoms. Okay? So how do I do that? Well, here's your 4 carbon atoms in a chain, butyl bromide. I make the Grignard. Now I add formaldehyde. I form a bond, just the way you saw, from the negatively charged carbon to the positively charged carbonyl. That's that red bond. And then the alkoxide on aqueous acidic workup gives me this tertiary alcohol. And that alcohol can be converted to a bromide using phosphorus tribromide, or HBr in this case would have worked too. So I go from 4 carbon atom bromide to 5 carbon atom bromide. What have I done? I've extended, so to speak, that carbon chain by 1 carbon atom. Okay, so that's a 1 carbon homologation reaction. Very useful thing to be able to do, although it does take several steps, as you can see. Now, 2 carbon homologation, same thing, but I need, instead of a 1 carbon electrophile, I need a 2 carbon electrophile. And ethylene oxide works really well. Remember that ethylene oxide reacts with nucleophiles. It's electrophilic, so I can get the nucleophilic addition to, and it's symmetrical to either one of these carbon atoms. Now I have the red carbon atoms derived from ethylene oxide, and then when I treat this with water, I end up with an alcohol that's got 2 extra carbon atoms. And if I started with a bromide, I can convert this to a bromide, and so on and so forth. And so by allowing a Grignard reagent to react with either formaldehyde or with ethylene oxide, I can extend the chain by 2 carbon atoms. Now it turns out, although your book doesn't say that, you can actually extend this to the 3 carbon too. This is less commonly seen, but this stuff here is also reactive, and you can buy it. And so this would give you a 3 carbon homologation. And it works almost as well as ethylene oxide. So you can do this chemistry for more than just 1 and 2 carbon. Okay, so this is an application of Grignard reactions. Now, this turns out to be important, as I said, because it allows you a way of making carbon-carbon bonds. Typically, you're not confronted. I mean, if you're working for one of these companies making drugs for hepatitis C virus, you're not confronted with, what happens when I add this to that. You're confronted with a different kind of problem. The kind of problem you're confronted with is this. Let's say that that this tertiary alcohol is something that the biologists want to test on hepatitis C virus. And so the biologist, of course, doesn't know how to get his hands on that. Well, unless maybe if they'd taken this course, they would, but, so he turns to somebody who knows how to do it and says, make me some of this. So you look at this, say, well, okay, it's tertiary alcohol. I heard something way back when about tertiary alcohols. How do I do this? So, as it turns out, for this tertiary alcohol, of course, there are 3 ways you can proceed. Here's how you think about it. I'm going to draw the structure. Again, I'm going to leave off those end methyls because we already know how those work. Okay, so this is our target. So the question is going to be, well, for a target like that, how do I proceed? So you can proceed in any way, any of 3 ways. So let's look at this bond first, okay? So I can say that, well, okay, I could have made this alcohol by having CH3 minus, that's that CH3, adding to some ketone. What is the ketone that I would have to add that CH3 minus to in order to get this tertiary alcohol? Well, whatever's left. So I'm going to draw this kind of a squirrely way. Okay, so this is what's left, right? Those are the carbon atoms, and there would have had to have been a ketone right there. Okay, so if I do this chemistry, then I will end up with that tertiary alcohol. So that'd be one way to do it, and that certainly will work. But that's not the only way. There are 2 other ways you can do it too. Why? Well, because I arbitrarily picked this bond and said this will be the methyl minus. But I didn't have to do it that way. I could have picked this bond here, this one, and I could have said, well, I could have had CH2, CH3 minus, ethyl minus, reacting with this ketone, like so, and that would have given me exactly the same thing. And nothing's changed. And in fact, there's a 3rd way to do it. And the 3rd way to do it is to start with 2-butanone and have butyl, Grignard or lithium or whatever, add there. And all 3 methods will give you the same tertiary alcohol. And so when I look at that tertiary alcohol, I need to be able to perceive all 3 different ways of doing it. Now, you can say that, well, in the company that wants the hepatitis C virus drug, they don't want you to do it 3 ways because that wastes your time. They want you to pick the best way and make a kilogram of it for them. So how do you pick the best way? Well, for us, that's a hard question to answer. It's not one we need to think about. But the way this works in pharmaceutical manufacturing, fine chemicals manufacturing, is as follows. Probably they would pick this method here, because remember, 2-butanone is a solvent. It's an industrial solvent, which means what? Which means it's available in bulk and it's cheap. So this is cheap stuff. Butyl minus, well, you say maybe butyl lithium is expensive. Yeah, it isn't cheap, but there's not much difference between methyl lithium and butyl lithium. And ethyl lithium, for whatever reason, is not quite as available. And so probably this would have been the method of choice. Okay? Just mention that in case you had questions. So the importance is that when you see a secondary or tertiary alcohol, that you be able to see this chemistry going in the reverse direction. Okay? So I want you to be able to say, oh yeah, this alcohol could be made this way, or this way, or this way. I also want you to know this 1-carbon and 2-carbon homologation business. Now, the next thing we're going to talk about looks almost exactly like hydrate formation. Okay? So, when we talk about hydrate formation at the beginning of the hour, what did we say? Well, we said that it's kind of boring, you know. So, okay, so here's hydrate formation, right? So you get acid transfer, activated carbonyl, nucleophilic addition, tetrahedral proton transfer, so on. Now, when we talked about water, whether it be as a nucleophile, whether it be as an acid, or anything else, what do we compare it to? Or whether we talk about boiling points, or physical properties, or IR spectra, what do we do? You know, we're talking about alcohol. We're talking about alcohol. So if it works with water, it should work with an alcohol too, and it does. And so what we're going to look at next is formation of acetals. Now, we find that, you know, protecting groups, we'll talk about what that is in a minute, but let's talk about acetals first. So, what is an acetal? Well, this is an acetal. So if I start with a ketone, and I use methanol as a solvent, and then I have a trace of acid, typically sulfuric, chlorine, sulfonic acid, could be other acids too, heat it up, and sometimes you have to remove the water from the mixture. But if you use this as a solvent, often not. This is an equilibrium, but I can push the equilibrium to the right by using this as a solvent. And so this would be acetophenone, dimethyl, methyl, acetal. Now, notice this carbon atom. This carbon atom is kind of strange. It's like the hydrate carbon atom in the sense that it is a carbon atom that is bonded to not one but two oxygen atoms. Okay, so you can think of acetal carbons, hydrate carbons, carbonyl carbons as being related to each other. Why are they related? Because this carbon atom is also bonded to two oxygen atoms. Well, bonded twice to the same oxygen atom. So it has two bonds to oxygen, two bonds to oxygens, and that means that these carbon atoms are, in some sense, equivalent. Okay. So acetals have one carbon atom bonded to two oxygen atoms. Now these reactions, unlike the addition of alkyl lithium or Grignard or whatever, these reactions are in fact reversible. And you reverse them with acid. So I have the Chatelier's principle, right? So if I use this as solvent, push the equilibrium here and isolate this. If I isolate this and I throw it into a bunch of water and I heat it up with acid, it's going to go that way. So that's a useful property, because what this tells you is that I can take a ketone and I can convert it into something that is not a ketone, something that does not have the reactivity of a ketone, and then I can convert it back to a ketone. So that's the concept that we're protecting. So I'm going to give it away a little bit. This carbonyl carbon atom, if I think about the resonance structure, this carbonyl carbon atom has a what kind of charge? Is a positive charge associated with this carbon atom? Well, not really. A little bit of a one, because these are electronegative, but it's not the same as that. So this will react with things like hydride, like sodium borohydride, lithium aluminum hydride. This will react with things like methyl lithium, like butyl magnesium bromide and other Grignards. This will not react with sodium borohydride. This will not react with lithium aluminum hydride, will not react with Grignards, will not react with alkyl lithiums. And so that means that it is protected from reaction. Okay? That's protecting group. Now, why you want to do that probably is obvious to you, but maybe not. So we'll talk about it. Oh, and by the way, what I just showed for ketones works for aldehydes too. A very useful acetal is formed from ethylene glycol. Ethylene glycol is what? Antifreeze. Yeah, it's antifreeze. And what else? What kind of properties does it have? Well, it prevents water from freezing. No, biological properties. Okay, so there's a very famous picture in one of the national parks. I think it's Yellowstone Glacier, I think. And the parking lot is there, and there's a bighorn sheep licking the ground. And it's licking up ethylene glycol that's leaked out of the radiator in the winter. And that's not good, because ethylene glycol is sweet. as are all compounds that have all glycols. Sugars are glycols, by the way. But ethylene glycol is also very poisonous. And so you can, if you ingest this stuff, it's not a good thing. Okay, so we've reached the end of our hour. We'll pick up on Friday.